we shall start our discussion on hydraulic machines, and in continuation of my last lecture, today again we shall try to solve another two problems from pumps. So, basically in the last lecture we have solved one problem on radial flow pump, and we have seen that by solving this problem we need to recapitulate the concept that we have learned from the previous classes, and while solving this particular problem that will help us to grow confidence on not only on understanding the fluid dynamics that is there inside the pump, but also to design the pumping system. So, today what we will do, we shall solve another problem, and this problem is again taken from radial flow pump. As usual, since I have taken this problem from one particular book, this is exercise problem and it is written centrifugal pump. So, that is why I did not disturb that term, but again I am telling I would prefer to say radial flow pump. So, let us quickly read the problem statement and then we will proceed to solve the problem. The statement is, a single stage centrifugal pump is to be used to pump water through a vertical distance of 30 meter at the rate of 45 liter per second. So, we can understand that the pump needs to supply water from one place to the other place, that particular place is located 30 meter above from the suction sump, and we also need to have flow rate at the rate of 45 liter per second. Suction and delivery pipes will have a combined length of 36 meter and a friction factor F of 0.006 that we have to consider while solving the problem. So, it is given that we have this information that the combined length of the suction and delivery pipe is 36 meter, and the friction factor that F is given, that is, you can understand F, that is Darcy friction factor we have learned from our fluid mechanics course, and that is 0.006. Both will be of 150 mm diameter, that is suction pipe diameter and the delivery pipe diameter are same. Losses at valves etc. are estimated to total 2.4 times the velocity head in the pipes. So, that is also given. So, we need to consider other losses due to the presence of valves, bends etc., and that would be 2.4 times the velocity head in the pipes. The basic design of pump has dimensionless specific speed of 0.074, that is very important, but for the time being I will not ask you all to focus on this particular point, since we did not discuss about this very important term in the context of pump operation. So, the specific speed I will use one particular formula. For the time being I request you all to accept that, but in one of the forthcoming classes I will be discussing this part in greater detail. And the pump is having forward curve impeller blades with an outlet angle of 125 degree to the tangent, and width of the impeller passage at the outlet equal to 1/10 of the diameter, that is also given. Okay. The blade themselves occupy 5% of the circumference. If manometric efficiency Nm, it is again I am telling manometric efficiency is also termed as hydraulic efficiency in some books. So, it is given neglecting wall strip. So, when we are calculating the manometric efficiency, we need to neglect the wall strip of 75% may be expected, determine the suitable impeller diameter. Okay. So, if we go to solve this problem, as I told you in the beginning, it is advisable to draw the velocity triangles that will help us to understand the velocity components, blade angle and the flow velocity. Okay. So, I mean if we quickly draw the pump impeller, So, we will be solving now problem. Right. So, this is say this pump is rotating in this direction, that is in the in the clockwise direction, and if we go back to the previous slide, it is written that the forward curve vanes. So, the vanes which are there, rather the vanes equipped with this pump are forward curve. So, we have to draw the blades accordingly. So, this is one forward curve blade, this is also blade, this is also blade. So, these are the forward curve blades considering the direction of rotation, that is again important. So, if we take out one particular blade, say this blade, if we take out, if we take out this particular blade, and if we try to draw the velocity triangles, if we try to draw the, so this is the blade, right. So, this is U1, this is W1, this is C1, and C1 equal to CR1, C theta 1 almost equal to 0, because we need to neglect the wall strip, right. So, this is very important statement we should look at, neglecting wall strip at the inlet. So, that is very important. We really cannot trivially ignore the wall strip at the outlet. So, when you are solving any particular problem, you should have a physical feel about the problem you are going to solve. So, you understand that wall strip at the outlet cannot be 0. If the wall strip at the outlet needs to be 0, then C2 will be equal to CR2. So, that is a special design, and I mean having a blade like forward curve or backward curve, it will not be possible to have nose wall at the outlet. So, this is the rotation, okay. And so, this is the inlet velocity triangle, and if we try to draw the outlet velocity triangle, it will be like this. So, this is C2, U2 is fixed, and this is W2. So, this is C2, this is CR2, and if I try to use different color, that will help us to understand. So, this is okay, and now I am using, so this is W2, okay. Now, you see this is U2, you can understand this is C theta 2. Now, so this is C theta 2, so basically component of absolute velocity in the tangential direction, and this will be what W theta 2, but this will be C theta 2 minus U2. So, if we try to draw the velocity triangles, and this angle is beta 2 equal 125 degree to the tangent, that is also given, okay. So, this is 125 degree. So, once we have drawn the velocity triangles, it becomes very easy to calculate or to proceed the problem, and finally to obtain the desired quantities. So, this is the this is the picture. Now, if you can draw the velocity triangles correctly, it will help you to solve the problem without any difficulty. So, now you can see what we need to calculate. We need to calculate impeller diameter, but we have to go systematically. So, you can see what first we can calculate. So, it is given that the flow rate 50 liter per second, that is what we need to ensure, that the pump will be able to supply water at this rate essentially by overcoming the losses due to friction, losses due to valves etc., and also the static height, that also we should consider. Okay. So, can we not calculate the velocity in the pipe? It is also given that the diameter of the suction pipe as well as delivery pipe is same. So, basically if we try to calculate the first step, that is velocity in both pipes. So, V I am writing V S suffix S comma D, that is suction comma delivery, that is nothing but 45 liter into 10 power minus 3 meter cube per second. So, this unit conversion factor is there, divided by pi by 4 into 150 mm. If we try to recall, the diameter is 150 mm. So, this would be very quickly we can write, this is 0.15 square, and if we calculate it, it will be coming 2.55 meter per second. Again I am telling, you should write the unit correctly, otherwise you may not get full credit. So, this is important. Now, another next part is, can't we calculate the total loss? Can't we calculate the total losses? We know that what is the what are the components we should consider while calculating total losses, Hs plus Hd, that we have learned. So, these are basically static height in the suction and delivery sides respectively, plus frictional loss, right, plus Hf frictional loss plus H minor. Okay. So, this is the total loss, basically in fact in terms of head we know this is also static height head, this is also head, this is also head, and finally the minor loss. So, minor losses. So, you can see this is given 30 meter combined length 30 meter. Now, this is very important, how can we calculate losses due to friction? We have studied in fluid mechanics the Darcy-Weisbach equation. We can simply use friction loss or losses due to friction Hf equal to L by D V square by 2G. Mind it, I mean this V we should consider loss in both the suction and the delivery pipe, but fortunately the velocity of liquid in both the lines are equal, is equal. So, this is V. Now, here it is very important that should we consider F or we can consider different coefficient. So, you have studied that this is Darcy friction factor. Now, I will be using 4F. See, this is also very important, that fanning friction coefficient. So, basically F is the Darcy friction coefficient. Sometimes it is also termed as Moody friction factor. Okay. So, you are familiar with this term, and you know this is called Darcy friction factor, but I am telling this is also known as the Moody friction factor. And now CF equal to, I am telling rather I will be using one extra term, say F prime, that equal to 4 into F. Okay. So, now I will be considering F prime. So, though these two friction factors are same in all other aspects, but they are differing. So, this F and F prime, these two friction factors are same in all other aspects, but they are differing from the perspective of the degree of accuracy while calculating the frictional loss. So, if we just include 4 times of F, maybe we know that when liquid is flowing through the pipe, the losses due to friction between the wall and immediate fluid layer and also between two adjacent fluid layers we need to consider. So, that frictional loss we need to take into account while calculating the total head that will be developed by the pump. Our objective should be to do such a calculation so that we can closely mimic the actual scenario that will be there in the real application. So, instead of calculating the head loss due to friction by F only, and that is also sometimes known as fanning friction coefficient. So, basically I can give it. So, this is F prime. Okay. So, this F is equal to, that is Darcy friction factor, and F that is nothing but 4 into F prime, say this is F prime and this is also F prime. So, this is F prime. Okay. So, this is F prime. So, instead of considering the Darcy friction factor, what we are going to calculate, I mean we are going to calculate F prime, and that is nothing but 4 F. So, again I am doing this, So, let us do this very accurately, otherwise it will be confusing. So, Darcy friction factor, say this is F and F prime, this is the fanning friction coefficient. Now, this is conventional. Why I am putting rather why I am trying to concentrate on this particular part. See, if you try to recall, here it is given F, but we know F is basically commonly used to indicate or denote the Darcy friction factor. Now, so if we simply consider, so let me erase it first and then this is erase it. So, now if we try to write, so now this F is not the Darcy friction factor, it is not given explicit information whether it is Darcy or fanning. So, typically I mean it is fanning friction coefficient. Now, we need to calculate, so that is why I would prefer to give F prime for this particular problem to denote the Darcy friction factor, and F is the fanning friction coefficient. Now, here we will be considering F, not F prime. So, this is this is F prime, not F. So, that is equal to 4 F L by D V square by 2 G, right. So, I am trying to concentrate on this particular part again and again only to make you understand that though these two friction factors, Darcy or Moody friction factor and fanning friction coefficient, they are same in all aspects, but still they are differing from the perspective of the accuracy while calculating the loss due to friction. So, now you can see if we just try to calculate HF by considering F prime, and that is what is given. If we try to calculate using just small f, then the head loss due to friction will be 4 times less, but if we try to consider using f prime and that is the 4f, then we will be trying to mimic, rather we will try to reach the, our calculation will be able to mimic the actual losses, actual loss due to friction they are in the real application. So, that is why we can easily calculate, that will be you can understand 4 f L by d v square by 2 g plus, if we give this name, this is equal to H f. Okay. So, this will be 2.4 times of that. So, now I can quickly write it, plus 2.4 into v square by 2 g. Erase it. So, I can write this is plus 2.4 v square by 2 g. Okay. So, if we calculate it, that is the total loss due to static height, friction loss and losses due to valves etc., and it is coming, total is coming 32.7 meter. You can understand that the static height is 30 meter, but other losses, that is loss due to friction and minor losses is 2.7. So, this is not very much. Even then our objective should be to calculate losses due to friction by considering this Darcy friction factor, that is 4 times of the fanning friction coefficient, though they are same in every other aspects, but still if we try to if we take 4 times of the fanning friction coefficient, probably our analysis will be able to closer, to the actual, we will be able to mimic the situation that is there in real application. Okay. So, this is the losses due to friction, fine. Now, see, you can see that is the head we need to develop. So, this is the head the pump will be able to develop while supplying water at a rate of 45 liter per second. Okay, fine. So, very quickly you have to solve again. Now, it is given specific speed, again I am telling, please do not be confused with the definition that I will be writing. So, this is N s equal to n root cube divided by g h power 3 by 4. So, please accept it that this is the definition of specific speed. I will definitely take one class to derive this particular expression, and then I will explain why this particular term is very very important in the context of pump operation. Okay. Now, it is given, you can understand, that is given 0.465 and that is n, we know 45. So, 45 into 10 power minus 3 to the power half divided by 9.81 into 32.7, that is the total head power 3 by 4. So, basically you can understand from here we can easily calculate what will be RPM. So, that is very important. So, N equal 166.2 radian per second. So, that is what. So, this H equal to 32.7 meter, that is what we have calculated from the previous analysis. Okay. Now, this is available. So, now next is what is flow area. Again I am telling that this is the impeller, it is having forward curve blades. So, this is basically, so So, this is flow area. Okay. So, you can understand this is d2 and this is B2. So, this is B2 width. So, what is flow area? So, this is at the outlet. So, flow area at the outlet that is, you know what is pi d2 B2, right. So, that is what we have learned. So, this is the flow area at the outlet. So, again I am telling, so this is the impeller and impeller is like this. So, this is the flow area at the outlet, okay. And pi d2 B2, d2 we have calculated, right. So, d2 we have already calculated, d2 we know because diameter of the suction and delivery pipe, we have to we have to calculate d2, that is impeller diameter, that is very important. So, what we need to do, we need to know B in terms of D, because ultimately we have to calculate impeller diameter, okay. So, if we consider impeller diameter at the outlet is d2, this is given pi d2 and B2 is 1/10 of the diameter, that is given, right. So, it is given that width of the impeller process is at outlet is equal to 1/10 of the diameter, right. And another important information is given over here is that 5% of the circumference is occupied by the blades, then actual flow area available will be 95%. So, that would be multiplied by 0.95, 100% is not available, 5% will be occupied by the blades. So, 95% is available. So, this is the actual flow area at the outlet, fine, good. Now, what will be flow velocity then? Flow velocity at outlet, that is CR2. So, CR2 into flow area, that is the flow rate. So, that is Q divided by flow area, right. So, this is Q by flow rate. Now, if we calculate it, if we go to the next slide. So, flow area equal to 0.298 d square. So, d2 square rather, because we are using d2 to indicate the diameter of the impeller at the outlet. So, d2 into d2 square will be there, and now CR2 will be Q upon flow area. So, CR2 0.045 divided by 0.298 d2 square, right. So, this is the flow area, flow velocity. Now, what about U2? U2 equal to R into omega, right. So, basically it will be coming already, I can write here not R. So, right, R into omega, sorry, I am this is R into omega. So, that is d2 by 2 into 166.2, already we have calculated, that is the omega radian per second. So, this is I am writing this is n, right. So, here I will be writing rather n. So, instead of writing omega I can write n. So, this is n. So, this is n. So, this is 166.2, this is again second inverse, right. So, radian per second, this is second inverse, okay. So, now you know that here another important information is given, that manometric efficiency is 75%. So, what is manometric efficiency? Now, again we will be doing over here. See this H actual equal some constant into H ideal, that is what we have discussed many times. So, this is manometric efficiency. So, therefore, we can write manometric efficiency equal to H actual by H ideal, and that is nothing but H actual divided by H ideal. What is H ideal? Using Euler equation, for the case where there is no swirl at the inlet, u2 c theta 2 by g. So, this is g by u2 c theta 2. Okay. And we have already calculated what is u2, we know what is c theta 2, right. So, here we can calculate, rather if we go, so that is eta m 0.75 equal to H actual, that we have calculated 32.7 into 9.81 divided by u2, that is just now we have calculated, that is d2 by 2 into 166.2, right. Okay. So, if we into c theta 2. So, from there we can calculate c theta 2, that is 5.15 divided by d 2. So, that is meter square per second. You can understand the unit of d 2 is meter. So, that meter and meter square will cancel, I mean will cancel 1 meter. So, that is meter per second. So, that is the c theta 2. Okay. Now, another next important task is, so we have calculated c theta 2. So, if we now look at the velocity triangle, okay. So, from the velocity triangle we can see this is shear 2. So, what about this angle? If I try to write using this, say this is this color. So, what about this angle? This angle is 180 minus beta 2, that is 55 degree. Okay. So, we know, so this is shear 2 and this is c theta 2 minus u2. So, from this trigonometric relation we can calculate that tan 55 equal to shear 2 divided by c theta 2 minus u2. Okay. So, if we calculate that, what is shear 2, and then so shear 2 we have already calculated, right. What is shear 2? Shear 2 we have calculated, shear 2 is the flow velocity. So, that is, this is the turn. So, if we try to write it, shear 2 will be coming 0.1508 divided by d meter square per second, again d2, again meter is there, and so basically, so that is d2 square. Okay. So, that is meter square per second. Now, so it will be meter cube. You can see is d2 square. So, meter square will cancel meter cube and 1 meter will remain. So, basically it is meter per second. So, we can write, I mean this expression, and that is 0.1508 divided by, you can see that is d2 square. Okay. So, this is d2 square, and what is c theta 2? C theta 2, that is 5.15 by d2 minus 83.1 d, right. 83.1 d, that is the value of u2. So, that is, you can understand 166.2 by 2, that is 83.1 into d2. So, now this is tan 55. Okay. So, now we have one relation, and that relation, I mean if we try to simplify it, we will be getting, I am writing over here, that is using, so tan 55 equal to 0.1508 divided by d2 square into 5.15 by d2 minus 83.1 d2, right. So, this is what we have written over here. So, that is d2. Okay. So, now you can see if we write the, if we calculate tan 55, eventually we will be getting one equation, and that is the cubic equation of d. So, 5.15 d, right, minus 0.1056 equal to 83.1 d cube. So, now if we solve this equation, we will be getting the value of d 2, and that is what is needed for this particular problem. So, now you can see by how we can do. So, first approximation what we can do, we can, you know, I can simply write this equation like this, that 83.1 d 2 cube 5.15 d minus equal to 0.1056. So, for the first approximation, we can make RHS equal to 0. If we make RHS equal to 0, we will be getting d 2 equal to 5.15 divided by 83.1 power half, and that is equal to 0.249, right. So, this is not the correct one, because we are trying to have approximate solution. So, this is first approximation, we need to iterate. Then what we can calculate, then what about, what will be d 2 cube? Okay. d 2 cube will be equal to 0.01416, right, and then because d 2 cube will be, I mean if we plug in the value of d 2 in this equation, right. So, d 2 cube will be equal to like this. So, this is we are obtaining from 1 by 83.1 into 5.15 into 0.249 minus 0.1056. So, this is, I mean we are getting d 2 cube is equal to this from this expression. Okay. So, then sorry, d 2 cube is equal to this, and then d 2 will be equal to 0.242. So, I mean if we try to go one step further, eventually you will be find exact diameter. So, we our first approximation, from our first approximation d 2 was 0.249, now we are having 0.242. We, even if we go for further, you know, trial, eventually when calculated value and approximate value will be equal, that will be the correct answer. So, exact diameter, if you do it, will be coming 0.238 meter. So, you can understand, and that will be equal to 238 millimeter. So, basically by solving, to summarize today's discussion, we have solved another one important problem that we have taken, and by solving this problem on radial flow pump, we have seen today that we had to recall so many things that we have studied even in fluid mechanics course. One important term that we have discussed today is that while calculating frictional losses, it is, I mean if you take the fanning friction coefficient, nothing wrong with it, but ultimately what will happen, the total loss due to friction that will be calculated, that calculation will not be the correct one, maybe we will not be deviating from the loss that is there in practical applications. So, our objective should be to calculate, while calculating total losses, to calculate the loss due to friction, taking the 4 times of the fanning friction coefficient. As I said, though other practical aspects are remaining same, but still they are differing from the perspective of the accuracy while calculating the frictional loss. And we have seen that knowing all those things, and again which helped us a lot is the velocity triangle at the outlet. And it is also important that it was mentioned that there is no swirl component. So, swirl component, I mean it is not explicitly given that the swell at the inlet is 0, but you have to consider, you have to apply your physical sense while solving the problem that swell at the outlet it may not be 0. If it has to be 0, then the blade will be of special type, but for the forward curve and backward curve vents, swell at the outlet will not be 0. So, definitely though it was not explicitly given that the swell at the inlet is equal to 0, you have to consider by applying your physical sense. Okay, so with this I stop here today and we shall continue our discussion in the next class. Thank you.